Well, welcome everybody. Thank you so much for coming. This is very exciting. Today is the launch of our new Green Economy Catalyst program. My name is Ian Overton. I'm the Chief Executive of Green Industries SA, and I would like to start with a welcome to country. So I would like to introduce, if Tiana can get past the photographer, I'd like to introduce Tiana Sylvie Williams.
Good evening, everyone. How are we today? Good? That's good. Nā marani nankinamira nai Tiana Katanya Sylvie Williams. Nature targetina bukyana kupuro. Na tanda nyanga yathuapi. Nadlako wara pirkuna nunawayatina kumayata nadlalo tamhanti. Yach nachina bukyanaku. Yata kamanka nathanatawilla. Yatako imprendi. Na wanganthi mani na budni gana yartana. Ladies and gentlemen, hello, my name is Tiana Sylvie Williams. I'm the firstborn female in my family. I grew up here in Adelaide, but my family are from Point Piers on the Yorke Peninsula of South Australia. Recognise my people's language, their stories, their dances, and their country. Recognise that we walk on the land of my ancestors. On behalf of Kumukaro and my family, I greet you to the spirit of place and I welcome you to our country. My friends, let's walk together in harmony. Thank you.
Thank you, Tiana. So we're here tonight to hear about Green Economy Catalyst program. Who knows what the green economy is? Oh, no hands. All right, well, I better introduce one. Thank you, sir. Thank you so much. One hand. The green economy is an economic model that is about economic growth and job creation. It is about improving the environmental and social well-being of our country, of our state, but doing so in a way that actually increases our economic productivity and our job creation. So it is sustainable and it is profitable, and it is the way for us to tackle climate action. So South Australia, Green Industries SA is supporting this program. We're launching it tonight, and we are hoping to run this program over years to come. It is all about escalating the green economy progress within South Australia and about bringing global leaders to Adelaide to engage with government, industry and community. We're trying to drive productivity and value creation as true to the green economy components, and we're after fast tracking to a circular and green economy. It is about scale and about pace. The world needs our action and it needs it fast. And the person we have here today is Professor Göran Roos. We are very privileged to have Professor Roos here today. I'm going to read it. Sorry for reading it, but there's an awful lot here. I could take up probably an hour just reading the bio, but I won't. Professor Roos is one of the founders of modern intellectual capital science and is recognised as a world expert in the thinking and practice of strategy and innovation management, as well as industrial innovation policy for advanced manufacturing and green economy. He is currently advising government agencies and companies in Norway on industrial policy, emphasis on Industry 4.0 and greening, innovation policy, and other technologies, capabilities across SMEs and supply chains, and with companies around strategies to benefit from the digital and green developments. Göran was named one of the 13 most influential thinkers for the 21st century. How about that? By the Spanish Business Journal. He is a visiting professor, and I shorten this, Göran, because I'm just going to name the universities instead of all the departments. Visiting professor for Cranfield, Flinders, Adelaide, and Chongqing universities. He is a fellow of SIRO, the Australian Academy of Technology, Science and Engineering, and Royal Swedish Academy of Engineering Sciences. Could you please welcome Göran Roos?
Thank you very much, and thank you for coming here, and thank you, Ian, for allowing me to be here. The key thing is to understand that two things. Firstly, we have to go green. I don't think there are many people who don't get that. The second issue, we have to understand the difficult boundary conditions of going green. There are numerous hurdles and numerous challenges that we have to overcome. And it is the combination of the challenges and the opportunities that provides the great economic opportunity that lies in the journey towards green. So, some of you know this, this is just where does the CO2 come from? And there are a number of things here. You can see that some sectors are really need to do something. Iron and steel production is one of them. The other thing is when we look at this, we forget value chains. So if I look, for example, at value chains, the food value chain, including use of land, production, industrial processing and distribution into hungry humans, that whole chain is about 25% of all CO2 emissions in the world. So depending how you cut this, you get different type of priorities of where you want to address this. But something needs to be done. So a circular economy that people talk about is a really good metaphor. And I want to emphasize that it is a metaphor because it is in practice, because it breaches some laws of nature. It's unachievable, right? You can work towards it, but you can never achieve it. And I want to emphasize that because sometimes there is some misunderstanding in the narratives here. So we need to work towards it with an understanding that it's theoretically impossible to achieve it. So I'm going to touch a little bit on what those challenges are. How many of you heard about the second law of thermodynamics? Oh, good. We got a scientifically educated audience. I'm really happy. Okay. So that is one of the key boundary conditions. The second law of thermodynamics basically says that, if I express it simply, disorder or chaos in a system constantly increases. And in order to maintain the original level of chaos or order, you have to constantly add new energy to the system. And that means that when you look at a circular economy, the first flaw it has as a concept is that it looks only on the material flow, not on the energy flows associated with those material flows. And when we think about how to move to a more circular economy, we need to have a perspective that includes both the energy side and the material side. And the energy cannot be recycled, or rather exergy cannot be recycled, but materials can. Then people say, let's look at nature. It's a wonderful thing. No, it isn't. It's unbelievably inefficient, right? It's a system that is full of suboptimized subroutine that are suboptimized in order for the whole to work, right? And it's extremely wasteful. It converts low entropy, in other words, resources that has a really ordered thing into things that are very disordered, right? And then it uses very energy inefficient processes, oxidation and so on, to move from one step to another. So when you went to school, you may have seen the triangle with primary producers and all those things. And basically, as a rule of thumb, 10 units of one generates 1 unit of the next, with a lot of waste on the way. So, 10 kilos of plankton generates 1 kilo of shrimps, and 10 kilos of shrimp generates 1 kilo of fish, and so on. And, huge of energy waste and all this kind of stuff. So don't look at nature as a template. It's really not a good template for some of these changes. Well, I'm not going to go through that, but basically what it means is we have to be careful about the models we pick that we're trying to emulate. That's the first message. If you really wanted to be theoretically correct and say, we are going to basically become zero waste, the only way you can get there is to reduce complexity to zero. And that would be a very nasty thing to do to most people, because that means the stop of any process that we have out there. So what it means is within the boundary conditions of the level of a complexity that we want, we have to be as little wasteful as possible. And that's a different take on it. Then people talk about green value chain. And there are many different uses of that. So let's look a little bit at what we mean by that. So there are green value chains that are, comes from green origins, forestry, agriculture, marine, all this type of things. They are kind of inherently green because they come out of a biologically green, sustainable raw material. And by the way, as a side issue there, the maximum carbon sink in a forest is not by letting it grow forever. It is by cutting it down when it achieves a maximum absorption issue and then replanting it, because over time, this carbon sink effect goes down. So that is why managed forests are better carbon sinks than non-managed forests, which again is a misunderstanding that frequently contributes in the narrative. And then you can go down the route of biochemicals, which is a brilliant route. You can create very many smart chemicals out of cellulose, and they can be substitutes for either saving the environment, like with the vanillin out of lignin, so you don't need to take vanilla out of the orchid, or they can actually replace, substitute for petroleum-based chemicals in a nice way. Or you can go down the atomic modification route and you get nanocellulose and transparent paper and other kind of interesting things to replace plastic. So all of these things have huge potential. And if you take the end value that you can create and divide it by the first value you can create, depending on your chain of ish, the division ends up between 50 and 5,000. So you can just visualize the amount of value you can create by creating a better green chain out of some of these things. I have to flip through again, I see here. There we go. The second level is when you work around the substitution of existing way of processing things. A good example of that would be bioleaching of minerals. So instead of crushing the rocks down to the smallest level and then using all the other energies to extract what you want to do, you do a rough crush, and then you pour some interesting bacteria or something over it that leaches through and absorbs the mineral you want. In Finland, there is a large nickel mine that operates that way. So it takes 2 years for the leach to go through. So you have to wait 2 years to start, but then it's continuous as you replace these things. And you get a biosludge at the end that contains very high components of nickel. It's very easy to extract. Right? As a country, if my numbers are right, and I may be wrong on the odd percentage point, but as a country, Australia uses about 8% of the total energy produced to crush rocks. Now, a lot of that energy is used by diesel generators and so on out in different places, but it's about 8%, give or take. And that is not necessarily a fantastically good use of energy, because that really enhances the embodied energy that you sell away at the end in your ore, which you don't necessarily charge for as such in this process. So you can do that. Then you can, as I said, that's an example of the chemical you can substitute in pharmaceutical production from cellulose, as opposed to one that comes from petroleum. Then you have value chains which involves the energy side of things. You have value chains that generate batteries or generate wind generators or something like that. Whether they are green or not is an interesting discussion. They are necessary for a green economy, but some of them are difficult to be green in their own right. I mean, how many are familiar with the recycling process for lithium batteries? Not a nice process, okay? You grind these things down, and you get something called black mass, and you pour a set of very nasty chemicals across that, and you then extract a few things that have a very high value on the market, very simplistically expressed, and the rest of it basically goes to landfill. Now, that's not a nice process, right? So we need to improve some of these things dramatically if we're going to move forward. And also heavily energy intensive. Just to give you an idea, if you're going to set up a gigafactory for batteries, which sometimes people wish you could do in Australia, which I brutally say you can't, because just simply you need, for an average gigafactory, you need 4,000 to 7,000 skilled workers. Now, where do I get them here? That's just a starting point. You then use, for every kilowatt of energy that you produce in a battery, you need about 80 kilowatts of energy into that plant. So it's hugely energy intensive. And then there are a few other things you need, like raw material access and so on. So it's not that easy to put these things in place. You need a number of things to make it work. So you may have some raw materials, but just not enough to get these things to work. And then, of course, at the end of the day, what we want to do is you have hydrogen we talk about, and I can come back to that if you have questions at the end. I have some views on that too. The one thing I do not want you to believe is you can export it. Okay, because most recipient countries like Japan and so, who will start taking some of you for it, has the capability to produce that hydrogen themselves for a cost that is lower than your production cost plus the transportation cost. So that's just not going to happen. Okay, so you need to value add to that. You know? Then every value chain needs to go green, and that is the big journey. You need to green up every single value chain that you have. And there is a process for looking through that, anything from renewable energy to recycling to efficiency to this, that, and the other. But it's, and I have a step process, but I'm not going to go through that. But that is where you see the real short-term gain in their economy. And then you have the issue, is it difficult or easy to do these things? Because it entails new technologies, new customers, new things to be set up in an industrial scale. And the answer is, it depends on how easy it is for that system to capture this new knowledge and put it to use. And we have a funny term about that called economic complexity. And basically, it's very simple. So what you look at, you say, for example, look at SA and say, how many places in the world can produce what you produce? That's the first question. And the second question is, so how many different products of the ones you produce do you export really well? Revealed comparative advantage is the technical term. So in how many of them have you got a larger market share than you ought to have given your size, right? And if the answer is yes, we have a lot of those, and very few other economies can do what I can do, I am a very complex economy, right? And there you find, you know, the Germanic countries, you find the Scandinavian countries, you find Japan, and so on. And you can measure these things. Now, if you have an economy that contains everything, if I come with a new technology, there will be somebody there who can capture it, understand it, and put it to use. If I have an economy with very few things, then the likelihood that they're going to be able to capture, understand, and put to use that technology, whatever it is low. So that means as if you have low complexity, you're always going to be behind on the ability to put new things to use. And that's the challenge with economic complexity. And because economic complexity is also a predictor of future economic growth. And it means, very simplistically expressed, that this law adheres to the 11th commandment. To those who have shall be given. Okay, that's what it means. Okay, it's increasing marginal return effects. So in economic complexity is a really great starting point for benefiting from volatility, uncertainty, complexity, ambiguity. It really is good for countries that have that complexity. They will take opportunities in this. Some things will go down, some things will go up, but on the whole, they will come up better off in the turmoil. But it's driven, and all this complexity we're now living in are driven by all those things, right? CO2 emissions can be linked to economic complexity because what it means is that as a country, as you go through this journey of getting more and more complex, you will emit, everything else equal, you will emit more and more CO2, energy use, whatever it is, until you get to a point where you're so complex that you start to put to use technologies in your own interest, self-interest, that reduces these things. And we know roughly, and I have some pictures, you can see for every country it looks around that, but the complexity turning point is around 1.4 to 1.8, right? SA is about 0.8, right? So what that means is that everything else equal, and it need not be, but everything else equal, the greenhouse gas emission from SA are likely to increase as you build complexity, which is necessary to put all these things to use before you're able to decrease it. So things are going to get worse before they get better. But unless you allow it to get worse, you will go nowhere. So the opportunities and challenges lies in these domains. So I'm going to quickly try to go through them, so bear with me on that. So there is something about recycling. The first thing that we have to accept is that the quality inherently of the material we recycle is reduced in every cycle it goes through. You recycle newspapers, the fiber length shorten, at some point it's not useful any longer. You know, so there's a general degradation in every recycling step. And in order to offset that, you need virgin raw material combined with energy. So that means that recycling is not that easy. And you need lots of energy for this, and you need access to virgin raw material. And, you know, as I said, if you have, you know, valuable material like gold is very well recycled. But if you use gold today, that is not coming straight from the mine, but coming from recycled, it still need to keep 1 kilo, you need to add 2/3 of a kilo. We are not able to recycle more than 1/3 in this system of such a valuable material. Right? And as we build our society, we get legacy systems. You know that we got roads, we got houses, they need to be maintained. So in an economy, the more complex it becomes, you need energy for what you already have that needs to be maintained, but you also need energy for the new things you put in. So we have an exponential increase of energy need as complexity increases. I said that, and some of those things means building new things, and that uses energy its own turn, so lots of things. There is also a couple of problems around what we can do. So there are some processes that are irreversible, that we cannot break, we can't reverse them. Making concrete or cement is that. You know, you cannot take it back to its components. It's an irreversible process. Right? Very difficult to get sand out of the concrete once you have made the concrete. Right? The other one is that we have things that we cannot, the technology is not there to recycle. You cannot on scale recycle permanent magnets that use dysprosium as a doping material, which you have in every electric vehicle. It's too little and it's very difficult to get it out. We have no technology today at scale that works. That is actually the limiting factor for how many electric vehicles you can build. Because in today's world, we have 1,800 tons roughly of dysprosium is generated every year, 90% controlled by China. It's a side stream of other things. So it's very difficult to up it. You need 100 grams per every car that you build. That means that if everything went to cars, which it doesn't, you can build a maximum of 18 million cars per year electric. Every year there are built 82 million cars in the world. So who are those people, the 3 out of 4, who will not be allowed to have a car tomorrow? These are limitations that we have to overcome in some way, inventing new ways, new technologies, new materials, whatever it is. That is the challenge. And then we have things that we can do this, but I said, you know, you lower quality material conversion with lots of energy and virgin material. And aluminum is a typical example of that. So if we look at this, we can say that recycling some products that contains Keynes material actually do not reduce CO2 emissions. They may even increase it because of the energy need, the material that you use in order to run it. And that's really difficult. And it's mostly an industrial and technological challenge around these things, getting better at doing energy generating capacities that are not in its own right energy intensive to produce and operate, and having maybe substituting some material that are scarce and difficult to recycle into these things. So these are boundary conditions and also opportunities. As we go green, we need electricity, and we need lots of it, right? And a big problem for that is practical things like what are you going to build to generate it? Important. And how are you going to move it to where it's generated, to where it's used? Huge infrastructure investments for this, right? And then, of course, you know, how are you going to integrate stable, so dispatchable electricity with variable electricity? Again, it's a challenging problem. And the moment you start to put in batteries, your energy return on energy invested gets really bad. And I can show you just to put a scale on this, very briefly. In Sweden, we have 2 companies linked. It's a mining company that produces iron pellets, and it's a steel maker that produces steel. That company makes 1% of the world's steel, 90% of the world's high-value steel. Well, very specialized steel maker. So they are now both going green. That means they replace coking coal with hydrogen. They're stopping making pellets. They make direct reduced iron and so on. This is incredibly energy intensive to produce the hydrogen and to do all these things that they need. So when they are finished, these 2 companies, they will draw on 2 companies. 45% of Sweden's present electricity production will go to those 2 companies. 45%. That's more than the whole country of Denmark in energy use for 2 companies. They will then reduce Sweden's CO2 emission by 3 percentage points. You imagine how much more electricity, well, I should say electricity throughout it, how much more electricity Sweden needs to produce to continue this transformation process of the economy. And then you can work out how many wind generators you need to do this, and the surface area for them, and the energy cost, and the investment cost, and all this kind of stuff, and taking them down when they're over, and all this kind of stuff. And it's really difficult, and it's very difficult to make anything, and you won't like this, anything but nuclear to make sense. We can also cut it by energy, by industry. So here you have a set of which are the big boys that uses a lot of CO2 per dollar of turnover. And you can see how CO2 intensive materials are. It's a really, and if you are in the materials business, which Australia is, that's where a lot of it sits. So for the average country, going green, depending on its economic complexity, will require multiplying the existing electricity generating capability by a factor of 2 to 4, between doubling and quadrupling. Now, that is not going to be a cheap exercise, but it's necessary. But the bigger cost is getting the electricity from where it's generated to where it's going to be used. That will cost an enormous amount of money. And then we're going to, as I said, we will need scarce raw material if we go electrification. No, when we don't have enough of it. And we're not very good at recycling most of those rare earth metals. So we will have to develop new technologies. Now you have a great thing. You have your tailings dams outside the Olympic Dam. They are full of some of these things, but nobody has developed a suitable technology at scale to extract that yet, but it has a huge economic potential. So there are many of these things that we may play with if we choose to do that. Here is an incomprehensible picture, but what we'll look is a number of squares there, and under them, over them is a substance, an element, silver, platinum, and so on. There's a black line on the left, and that's it's where our present production development is. Then you have a reddish area, and that says where the future will require it to be in order for us to go green. It's a bit uncertain where in the area, but somewhere in that area it is. And you can see some of these are not a problem, some of them are a major problem. That is the boundary condition of limitations of nature. Right? And that also changed the geopolitical balance. So suddenly we go from being dependent on countries which has fossil fuels to countries that has metals. And you can see the difference from there to there. And of course, the red one is China. China has very cleverly, under a very long period of time, worked to control some of these critical materials. And that will stand them in very good stead economically as you move forward. Australia, luckily, is on the map. It's a good thing. Right? Many countries are not. Which is why the Americans from the strategic metal list have decided to pay for some of your exploration activities to try to identify alternative sources, which is understandable. This is a bit of an older picture, but it's the principle I will look at, and I have all my disclaimer at the bottom there. There is a concept known as energy return on energy invested. So if you look at building an energy generation thing, a wind turbine or something like that, you know, it takes energy, raw material, refining, construction, putting together, taking it out there, taking it down, recycling it, all this kind of stuff. And if you then look, how much energy do I get out of this thing divided by how much energy it takes to make it, you get the ratio. And it varies a bit, you know, when this picture was done, it was about 4 for solar. They're all working, getting better. So not an issue, they're all working a bit better. But many of them are today below the level we require in civilization to maintain our present level, and that's 12 to 1. So if we are not getting 12 to 1, we have to decomplexify. And you remember what that meant, okay? And so if you look at this, you can see why our economy was based on gas and coal and so on. Yeah. And you can see the only thing that are higher are hydro and nuclear. So hydroelectric, Norway, fantastic, you know, not a problem. Nuclear, France, fantastic, not a problem. But if you don't have those two and are going to get rid of your fossils, you have a challenge. Yes, that's correct. And I just giving you a reference if you want to have fun there and look it up, because there's a very big study, very fresh study made on all this, and it just shows it is impossible for most countries to move to traditional renewable energy sources and maintain their present level of civilization. Look at it as a challenge. Yeah? Yeah? This is where we stand today. The good thing is we are very good at developing new technology and issues, but we can see where the opportunities must be taken to do this. Right? So the other thing is financial institutions are starting to look at this. They don't like to finance coal mines any longer. So there are a few things happening there, pushing us to do that. There are some value chains that will decline, some will grow, and you can see what you need to do it well in the future. Electricity, scarce input materials, high share of value adding, deep pool of competent labor, demand side policies to create new markets and develop the scale of them, appropriate and cheap infrastructure that is necessary for all these things, and fast and transparent approval processes. Can't take 10 years to get approval to do something. So there are some things in that. And you need to put some macroeconomic requirements, you need some physical requirements, some social adjustments, some institutional things. All these things we can deal with as such. And firms themselves need to do things. And I will start here to talk on Monday when I'm here and then I fly out. I will talk about the journey companies need to make in order to generally green up profitably their business. Two outcomes, greener and more profitable. That's what you're looking at. So it is a necessity to do all the activities to become greener. But the opportunities can be realized only if you understood the boundary conditions that put limits on them. You can't say, we're going to get rid of all diesel and petrol cars by 2030 and replace them all by electric vehicles, because it is not possible. It may be politically desirable, but it's just not possible. So you have to say, and it's going to be fine. Electric will love it until they get up to 2030, and you ask them, now 3 guys out of your 4 wouldn't have a car. So you agree who is that going to be? Right? So I will conclude on that, but my message is actually positive. My message is going green is a necessity and an enormous opportunity. It allows many new companies to do well. It allows us to create correctly much more value in our economies. But we need to understand where the challenges are, partly to see if we can do something about them by innovation and technology, and partly so we don't try to do something that is impossible to achieve. That is only disappointing. I can guarantee it. Thank you. I'm happy to take questions.
Thank you so much for that presentation. Inspiring or challenging, I think. I love the point when you just paused and then said, treat it as a challenge. I think that was excellent. We do have time for a Q&A. We do have a number of participants online, so I encourage you, if you would like to put your questions into the Q&A session on the online. But do we have any questions from the audience? Good. One from Craig.
Thank you very much. Yes, it was a very challenging discussion, really, particularly around energy, because South Australia's story is one of renewable energy transformation. Yep. So I'm really intrigued about this sort of tension you've raised around that we have to electrify everything quickly in order to get benefit, but there are all these impediments potentially around renewables. Is your story, in terms of the data and the frame that you've set, is that one that is sort of more global and perhaps European, North American focused, or is it actually relevant to South Australia, which in terms of resources, in particular wind and solar, mean that we've got perhaps a competitive advantage that other places don't have?
You definitely have a comparative advantage in wind and solar. You're not the only one with comparative advantages like that. But what you have is a lack of a comparative advantage is the distance between the point of generation and the point of use. So if you look at the energy cost of building those solar and other type of things, fine, you know, so we know what it is, it's still a positive return. Then you generate your electricity, but then you're going to move it from that very, very distance. That means you need to put in to have some minimization of loss. You put in high voltage direct current issues, losses cost about 2 to 3 cents per kilowatt hour and kilometer, right? You have many kilometers. Yeah, that means that, and that's a lot of energy to produce that material that goes in that transmission system. And if you add that cost of energy cost of the transmission system to the energy cost of building and operating the generation system, your perceived competitive advantage may disappear.
Is there a story there around abundance? Like, because sun is unlimited, we actually can produce to the point where some of those barriers are overcome?
Well, that depends on the energy required for the creation of everything that goes into making a solar cell or a concentrated solar issue. And at the moment, there is lots of energy needed for doing those. So not until we find other materials that uses less energy or other processes that takes less energy. And if you look at virgin raw material, every new mine you find basically has a lower yield than the existing ones, therefore will require more energy to extract it. So it's a kind of bad direction. Now, you still have a positive return, but I wouldn't overplay it. And if you then insert a battery, which you have done, you know, the production of energy view of that battery is a really big chunk of energy to get into that one. And that is also a complexity. So the problem here is where you put your frame, and that is the issue. So frequently we put our frame on too low and narrow an area. So we say that, oh, I built a solar farm, it's extremely profitable, and you know, I paid this for materials all gone, and it's wonderful. But I haven't actually worked in the energy that took all the way from there to get there, because I haven't really paid for that in the way it's been done, right? Most of my cost that I paid is others, but it's the energy that we have the problem with. So electricity primarily in this. So that is the challenge. So we need to rethink this. And that is why if you go a hydrogen plant, you need to put it next to those electricity generating facilities, because otherwise your transmission will kill it. So, and then you need to take that value added energy embodied substance, make it ready for transport by turning into ammonia. And then you need to go somewhere with it. And then you need to value add to it in some clever way. Be that by catalytically converting it back and putting it into a steel mill to do a direct reduced iron or something like that. You know, it's whatever you would. You put in a chemical plant, so you need to have it as a value add. So when you get a high margin on top of the price for your embodied energy when you sell it to somewhere.
Thank you, Roz.
Thanks, Ian. Thanks, Göran. It's lovely to see you back in South Australia. Just a quick question then. You talked about complexity of a society, and you talk about recycling. And obviously, the graph that you gave showed recycling of a final product going back to its original components. But in a complexity state, you would be taking that on to next use. At what point do you say that is recyclable?
Well, it's reuse and recyclability. So let me take an example. If you go and buy a Volvo truck, right, the components of it, you know, bars and stuff, are bolted. They're not welded. And that is how they have designed that there should be a reuse of these things. So when it's finished after it's 1 million kilometers or 6 years, what is average for these big ones, it goes in and it's disassembled, you know, and it's easy to assemble it. And every component has then a journey. So they know exactly where to go. So the big metal chunk in the engine goes back to be remelted and used in future engines. So that's a recycling journey for that one. The big, you know, iron chunks underneath, they go into construction industry for specific use. So there are very few components when it comes back in that doesn't have a dedicated journey. And that is how you maximize the value on the next step, by figuring out in the design process of the truck, what use could I make of these things, and how should it then be designed in order to maximize that use in the next step? So that's a reuse process, but some of them you can't reuse in anything, so you then recycle it. And of course, the more you have of local uptake of potential use of this, the easier it is to make a profit on that journey. Whereas if you have to have large transport to send that thing somewhere else, you may not have a customer because the cost will go up so much. So a complex economy, again, is beneficial there because it gives you that choice of recycling and reuse, because you have a multitude of variation of potential industries as uptake for that. So again, that is why complexity there is a better thing. Yeah.
Thank you. Question? Yes.
A great presentation. I feel that there may be something missing from the conversation. Is that, do you think that we should be having more focus on our overconsumption and that we should be optimizing our assets so that we're using less and being smarter about our existing assets because that energy has been spent?
If you talk it on a corporate level, the answer is absolutely yes. We should minimize waste, which companies generally focus on. They may not always have focused on, they have sometimes had the same challenge as people talking about the circular economy. In other words, they've focused on the material flow waste rather than the energy or even information waste in that thing. So there is but generally companies should focus on waste minimization. That's absolutely clear. When we go down to the individual level, it is easy to say that we ought to do that we might all agree with it, principally. But it's going to be one of these things where we say one thing and do another for many of us. And then we're down to human behavior and understanding behavioral economics and all that stuff around this. So you may say to somebody, I can say to all of you, okay, guys, no more coffees, because that is a really bad thing for the value chain, the supply chain, and everything. So you need to be good to nature by giving up your coffees. Huh? That's an overconsumption. How many coffees do you need in a day? Right? How many of you, some of you may say, I will minimize that. How many of you will do it? Right? So that is the challenge. We have to be realistic about human behavior in a number of aspects. On the corporate level, where we have a more rational approach to things, it is easier. So that, but also remember that there is it depends on the environment we live in. So we used to live in a world where companies thought about things like just in time. Okay. And that was because there was functioning systems, everything worked. Now we live in a world where it is huge disturbances, right? So if you have a company, you no longer think just in time, you think just in case, okay? So if you have a chance to buy a raw material, you buy everything you can, okay? Because the cost of capital of having the stock is lower than the opportunity cost of not having anything, right? So that means that we now have a higher level of waste inherently, but it's driven by the consequence of the scarcity, environment, and unpredictability that we presently live in.
Thank you. Another question?
Thanks very much. It's great to see that global view. Similar to what was just asked on the resource efficiency, when you're talking about those global electricity needs to power the economy, is the model taking into account a serious impact of efficiency, of energy efficiency, along the lines like the IEA said?
Yes, it's
50%.
IEA numbers.
It's IEA, so that's including like a 50% reduction on what we use to have the same productive output. So there's all part of the sums.
Yeah, it's all based on IEA numbers.
Yeah.
But again, it's an attitude issue. When I moved here and bought a house here, I lived there for 7 years. I was told we do not need isolation because it is warm here. I have never frozen so much in winter as anywhere in the world, right? And there seemed to be conceptual misunderstanding that insulation works well to keep the cool in, as well as keeping the warm in. But that doesn't seem to have permeated the way things are done.
So a very strong message to meet those targets, completely away from behaviour change, is the regulation that makes you have a minimum standard on a house. So there's a big movement here at the moment.
But that's good. Remember what I said. The things that make change on outcome is procurement, regulation, and agglomeration economic benefits are fully clustered.
So that
Those are
rather
the three
than
things.
having to give up your personal coffee as a metaphor, you're no longer allowed to build a house that will let the air
That's right.
leak in and out.
Unless you build it and then go bankrupt and it is there. Okay, technical issue. Yes.
Okay, I'm just going to go to one of the players at home. Mary has asked you to expand on your comments earlier about the potential of an export industry in hydrogen for South Australia.
Well, as I said, if you're going to have an export industry, there are two requirements. Firstly, that is something that on which there is a scarcity on the global market. Secondly, that you have a competitive price for what your alternative is. And the hydrogen at the moment, there may be scarcities. The demand is not enormous, but in some sub areas there may be scarcities. There isn't a lot, but there may be some. But you definitely, what it means is that if there is a scarcity, if there is a demand, there will be a supply. So there may be a temporary period, for example, in Japan, where they may need hydrogen from abroad whilst they build up their own hydrogen production. Japan is windy, okay? They have industrial capability to be wind generation. They have access to water, so therefore they can make hydrogen. And when they make hydrogen, their cost, even though they have a higher cost structure, maybe here, I'm not so sure about it when taking efficiency, but assume for a minute they have a somewhat higher cost structure. Still, even if your cost of hydrogen itself is lower, you have to have the cost of transporting it over to Japan. And normally what that means is a two-step process, to ammonia, in a vessel, and back from ammonia. And that means that that cost of the final hydrogen will exceed the cost of the locally produced one. Why should they then buy from you except for the stopgap period until they got their own in order? And so that is the challenge of hydrogen on its own as an export. Instead, what you need to do is to build it into something else. So use it to create value in something else that fulfills these requirements. Scarcity on the world market and or a better product at a lower price.
Sharon, do you hear? In your presentation, you explained the economic complexity and the impact in green economies. And you also explained that the South Australia have this 0.8 degree of economic complexity. In your opinion, what are the industries or sectors that could be targeted to improve that score to produce a quick win in the green economies?
Yeah, there are very few quick wins, but we can for anything. But let's go there. So what you do is you look at these sectors you have which fulfill two requirements. They are large and you have a revealed comparative advantage on the world market. You will find on some of them agriculture and a few things like that. So you would have those sectors. And then you say, how can I increase the complexity of what is produced in that sector? So for example, I stop selling peas and start to extract the protein from the peas. And then I say pea protein to the next step. And maybe I turn that pea protein into an alternative burger. And then I sell it. Then I have higher complexity. And I may produce a product that very few others in the world produce. And I will leverage my previous revealed comparative advantage to achieve a comparative advantage in that product. Then I have moved the complexity of that sector. Does that make sense? Yep.
You mentioned a few times about electric vehicles and that one of the problems is that only 1 out of 4 people would be able to own one. My first thought to that is, what if the 3 out of 4 just rode a bike or had an e-bike? And so I guess I've got 2 questions. One is, to what extent does reorganizing cities and does planning have an impact on some of the things we've been discussing tonight, in the sense of making cities that people can walk or cycle in? And secondly, whether or not, from a materials perspective, the other 3 people owning e-bikes would be feasible or not?
Well, firstly, it's a really good question and it's a really good point. So what will happen likely when we move into that electric space is that because it will combine with other movements, it will combine with autonomous vehicle development and so on. So you will have, firstly, you will have fewer people needing to own a car in urban areas. Let's talk urban first, where all this can happen. And then you can have, theoretically, you have your car, which you own if you do want to own one, that takes you to work. And once it dropped you off, it doesn't bark. It goes into robotaxi mode and makes money for you while it operates around that. So there are numerous developments that are going to come along here, and you will need to change the planning, and it will still enable transport if you live in an urban environment. It's the non-urban environment which is the problem. You know, if you want to have charging station every 300 kilometers on all the roads in Australia, you're going to go bankrupt, right, as a country. That's just not feasible, right? So that means that you can't have those type of electric vehicles out there more than a certain range from the urban area. Then you need to think of alternatives to that. You know, are you going to go down the hydrogen route, in which case you still need to put infrastructure in, they may go further and so on. So there are a number of alternatives there, but you have to separate the urban scenario from the rural scenario. You also have to separate temperature domains. So the great thing about electric vehicle is in this temperature, it's fantastic, right? They did a trial in Norway where they took all the bottles, and Norway has a lot of electric cars because penetration is about 70% on new sales. And they drove them on a cold day in Norway, which means many degrees minus, right? In a very hilly landscape. And then they drove them until they died, okay? And then they measured that distance versus the official distance. And the outcome was end result between 20% and 60% of stated distance, right? Now you think of that vehicle with 20%. That doesn't work. So there are other things we have to overcome in this domain.
Oh, hello. With the disclaimer that it's been 25 years since I did thermodynamics at university. And if there's any physicists in the room, someone can help me out. But my understanding is that when you've got a closed system, then the laws of thermodynamics that you're applying, that you're saying applied. But if you're able to take energy from outside the system, then you can at least temporarily decrease entropy using the energy that you're taking from outside. And so my understanding of a circular economy is that we're aiming to use waste streams not in the same way as, like not in a reversible chemical process or something like that, but that the waste products from one thing feed into another thing in a circular way, and our economic sectors are integrated. And the energy that's used to do those conversion processes, if it's coming from the sun, then it's coming from outside the closed system. And then the issue doesn't become, do we need to recycle all the energy inside a closed system because we've got an external source? And also, I lost it, but
no, I see
all the framing of it, I was like, I'm not sure that it has to be framed that way.
No, it doesn't. But let's take the argument for step one. Is the thermodynamic second law, does it talk about a closed system? Yes. So the question depends, where do you put your frame, right? So if you put your frame of Earth and Sun together, it's still true, yeah, because the Sun burns itself out in order to generate the exergy increase on the Earth. It takes a long time, but that's what it's doing. So its potential future is there. So the principle is still true. Now then let's look at the practice. So if you say, I'm looking at a system where I have non-reversible processes, which is quite common. In the real world system, you have that. Then you still need the energy to maintain the complexity in that system, the order in that system. So where does it come from? Well, at the end of the day, it comes from the sun. The question is, what level of losses and processes are you having in the system? And you still need, in a system that you outline, you know, you input from one goes to the next, you still need the virgin raw material to complement the reduced quality of the recycling and so on in doing that, and the losses in the processes, even that whether it's biological or energy, you have your oxidization process and so on. And that means the question I have to ask, is it possible to generate energy in some way that doesn't decrease in other words, that generates more energy than we need to use to generate it within the framework of what we can capture from the sun, either directly or through our biological systems? And the answer is sometimes yes, sometimes no. Yeah. So the answer is, the quick thing with your question is a good question, is the right question. The answer is not always yes. That's the problem.
I'm going to go to the last question online. It's a nice, easy one by John Phillips, which is, how do you cut through the unacceptable 10-year timeline of, and I won't mention the agencies, but governments to work towards new and innovative technologies?
have no idea. Okay, that's
Good.
my short answer. What it means is, remember what I said, it's approval processes. And also you have to realize the timelines in taking something from a discovery in a university into a industrial production issue, going through what is known as technology readiness levels. If you go through 1 to the 9, which is where you want to go, the average time that takes for, and which is enormous standard deviation, but looking at the American DoD, all those projects and looking at all of them, the average is close to 270 months, okay, to go through those steps from idea to finished products. Right? That's a long time. That's 20 years, right? Yeah. So it's inherently not very easy to speed these things up. So you don't want to extend that time period further by having very complicated approval processes that takes 10 years, right? So what you want to do is you want to shorten the process times you can have, right? In order to accept that certain things really are very difficult to do. And in some new areas, you not only have to go through a technology readiness of what you look for, you also have to go through something called manufacturing readiness, because the equipment may be not there that you need to produce the things that you have now discovered that you need to produce. So then you need to invent and develop the manufacturing equipment as well in parallel to these things. You can still probably fit it more or less within the same timeline, but the cost just went up dramatically for these things. And there is a cost multiplier for each step as well. So the answer is, I can't answer what you need to do specifically to cut through this, but the principles are, you need to minimize the things of time that you can minimize, but you have to accept that certain times is just not possible to do anything about.
Thank you. Look, we've run out of time, but could you please join me in thanking Professor Göran Roos again? Thank you. So that was the launch, the first event of our new Green Economy Catalyst program. Up on the screen, if you're interested to be kept informed, we will have other events coming up. This event was developed very quickly, and I really want to thank the team at Green Industries SA. In particular, I want to thank Veronica, Orsa, Matt, Bernadette, and Sharon for dropping everything basically and getting this together. And it went without a hitch, except for a little bit of gap in the slides, but we got through that. So thank you very much. I'd now just like to introduce Chris Kirk, who is from Stone and Chalk, and he's just going to welcome you here.
I get the best job for the whole night, and that's to remind everyone to stick around for a very carbon-intensive drink after this. Thank you, Professor. I have the absolute privilege here of running the Startup Hub at Lot 14. There's about 1,400 people now in this precinct, many trying to tackle some of the problems that you spoke of tonight. And I could see entrepreneurs madly taking notes. It's rare that in a 40-minute odd session, you get presented with so many consequential opportunities. So that was fantastic. Thank you. For those of you that haven't been to an event here at Stone and Chalk, we're running about 300 a year now, and many are on either this topic or related topics. So I do encourage you to get involved. I'm really excited about this series. We were just talking with the Green Industries SA team before about how exciting it is to actually be able to have international guests like the professor here face to face. So please, I encourage you to get involved. And yes, do stick around for a drink. And I'm delighted to say that I don't have to give up coffee, because I was getting deeply concerned with that just before. But thank you, everyone, and enjoy your evening.